Okay. So the session's being recorded now. So sorry for the people who are not here. They missed the first 2 minutes of my lecture. But we're just getting into what is the important thing with this slide. So I'm just reminding everyone at home, make sure you know all the properties of a laser that we discussed: monochromaticity and coherence and directionality and focusability and intensity and things like that. But in this lecture, we want to talk about this monochromaticity property, the property of having most of the photons at a certain energy or color. Mono meaning one, chromaticity meaning color, the property of having a color. And that makes a laser really special because it might not be as bright at all the wavelengths, meaning the total power, right? As we said before, a helium neon laser that I use in my lab, which kind of looks, it can be brightish when you look at it, is about 2 milliwatts of red laser energy. But when you plug in a light bulb above your head, that's 100 watts, right? A light bulb that I screw in is 100 watts. And this laser is like 1 or 2 milliwatts, right? So it's thousands of times less, tens or hundreds of thousands of times less in power. But this monochromaticity idea is that all of that power is concentrated into one color. And then, of course, there's no heat either, right? The 100-watt bulb, as Kane said, a lot of it just goes into heat, and that's just completely wasted. The laser does produce heat, but not as much heat. And the power that it does produce as photons are all concentrated at a single color. So if that color is what you want to use, it's much more efficient, right? Because the bulb is putting out light into all the different colors, and most of them are not going to be doing anything for you. So it's just like wasted. It doesn't hurt that they're there, but it's wasted. It doesn't do anything for you. So it's inefficient. So the properties of these lasers are all the power goes into this one color, and that color is exactly what you want it to be for a certain application, all right? And then that you deliver a lot of that energy at that color, way more than the bulb does. And so Kane had this figure in her book about the spectrum, showing the spectrum, which is the distribution of power over wavelengths of an argon ion laser or a light bulb, which is very broad. Argon ion laser is the peak. So that is really one of the important properties of a laser, that all the photons have a certain energy or color. And if we can match then, what I'm showing down here, if we can match the color of the laser to an application, then that's awesome. But we can't just pick random colors. We have to pick a color that will be matched to the application due to the absorption of the tissue. So we have to talk about what is absorption. So we can have a laser of a very specific color, and it can be very, very powerful. But if you shoot it through the air, it doesn't do anything because it's not absorbed by the air. So the power in those photons just goes right through, and that's not useful at all. So in your understanding of what the laser is doing in the body, or in any other material, but we're talking about medical applications, so in the body, you have to remember that for that laser energy to be efficient, it does need to be absorbed by the tissue. And some tissues are transparent to certain wavelengths, and some absorb certain wavelengths. But for the laser to impact that material, for it to transfer photon energy into the material needs to absorb it. So what we need to understand is the molecular chemical underpinnings of absorption. What do we mean by absorption? So let's dig into that a little bit, shall we? So we're talking about absorption, and then we're talking about color. So we have to introduce this idea of the color wheel. So the way we generally think about the color wheel is this. I'm going to talk about color, and then I'm going to talk about colors in reflection. So typically, when we think about colors, it is sufficient, not necessary, but it is sufficient to say there are 3 primary colors. All right, and so I have one of the color wheels, the color wheel in reflection, right here in the middle. And the 3 primary colors that we have kind of arbitrarily chosen are shown on the screen as red, check, green, check, and blue. So those are the primary colors. And if you guys are all looking at me on a monitor right now, so all of the monitors are showing color images to you because they have pixels in the monitor. And those pixels, each pixel is subdivided into subpixels of red, green, and blue. And any combination of red, green, and blue can then create any color that you want. So those are the three primary colors that we have kind of decided upon. So primary, RGB, red, green, blue. That's the way you write it. And so those are the three kind of colors, but of course you understand there are all colors of the rainbow, but we're going to be talking about the construction of colors by adding and subtracting these colors together. All right, so the first thing to understand is that white light contains all colors equally. Okay, so you know that. You know the rainbow, Roy G. Biv. White light is the combination of all the colors together. But in the construction of the color wheel, where the addition of the three primaries is there, it is sufficient to say that the addition of red, green, and blue, which is all the three primary colors, then gives white light. So what I'm showing here is all the colors of the rainbow, which is some even mixture of red, green, and blue, which kind of creates everything. Something which reflects all the colors equally well under white light illumination will appear white. All right, so if you illuminate something with all the colors, which is white light illumination, and that's what I'm trying to show with this rainbow arrow on the left, if it reflects all the colors equally, that will appear white. So on the screen in front of you, there we go. In my picture in the lower left-hand corner, I'm showing a white piece of paper. Why is this piece of paper white? It's because they have bleached it with chemicals, chlorine, but it's a form of bleach, and the bleach absorbs nothing. So whatever light hits this white piece of paper, all of the light reflects. Red reflects, green reflects, blue reflects. And the way our eye perceives that is that it's a mixture of all the colors, and we perceive that as white. So something which reflects all the colors appears white. And that's the way this color wheel kind of works. If it equally reflects red, check, and green, check, and blue, check, then you're in the region of this color wheel where all three of those things overlap, and that's white. So this graphic in the middle of the screen is called the color wheel and reflection. Conversely, again, white light containing all colors equally. So if you illuminate something with white light, as I'm showing here, and if it reflects no colors, so you're illuminating it with some equal mixture of red, green, and blue, it reflects nothing, that will appear black, right? That is what black is. It is the absence of light. So I'm asking you to imagine like a white sweatshirt and a black sweatshirt. They are both illuminated with the same kind of white light. To your eye, why does one of them appear white and one of them appear black? The white one appears white because it has been treated in a way that whatever molecules are in the fibers of the sweatshirt reflect all the light that's incident on it, or most of it, and that makes it appear white. On the other hand, the sweatshirt that appears black has been dyed. Dyes are molecules, right? That's how they make colored clothing. That's how they make colored anything. You dye it. It has been dyed with chemicals that strongly absorb everything that's incident upon it. So although you illuminate those two sweatshirts with the same amount of light, the black one doesn't reflect almost anything. To your eye, that appears black. So now in the color wheel upon reflection, we have moved out of the center. Now we're in an area where nothing gets reflected. So this is all is reflected. Out here, nothing is reflected. And then, of course, the colors inside are going to be when some colors are preferentially reflected, which we're going to get to in a second. So we have now explained why a white sweatshirt is white under white light illumination. We have explained why a black sweatshirt is black under white light illumination. What about a red sweatshirt? All right, you can certainly, some of you are probably, like one of you, if I could see you, is probably wearing a red sweatshirt right now. There are red sweatshirts for sure. Why is it that a sweatshirt under white light illumination will appear red to your eye? If it appears red to your eye, that means it reflects only red. That makes sense. So let's just follow the logic with me. It's not hard, but you just got to get it straight. So if it appears red, then it reflects only red because you see the color it reflects. That's what gets to your eye. The logic is if it reflects only red, that means it must have absorbed green and the blue. Because remember, you are illuminating it with white light. So if it reflects red, that means it strongly absorbs green and blue. So you have treated it with some molecule, some dye, and the characteristic of that dye is it strongly absorbs blue and green light, because you cannot make a molecule for reflection. What molecules do is they absorb the photons. They absorb the photons or they ignore them. So this is all about absorption. What's going on in the material. So something which appears red reflects only red, which means it absorbs green and blue. And then the same thing has to be true for blue and green, right? So if you're wearing a blue sweatshirt, that means it strongly reflects blue, but you've illuminated it. We're standing in a room with white light. So a blue sweatshirt has been treated with chemicals which strongly absorb red and strongly absorb green. And of course, green has to be the same way. So this idea of absorption is if this is the thing, you know, if this sweatshirt appears green to you, whoopsie, don't do that. If the sweatshirt appears green to you, the color we're on reflection means you go to the opposite sides and say, well, that means it must absorb the things on the opposite side of that wheel. So that's how the color wheel in reflection is used. Does anyone have any questions on that? Okay. So in the previous example, I was showing you these just interactions with the primary colors. So if it absorbs red and blue, it appears green. If it absorbs blue and green, it appears red. But what if it only absorbs one color? That's how you get these secondary colors. So something which absorbs one color from white light illumination, this looks like this picture is not quite right, but that's all right. This is supposed to be white light illumination, so that picture is not quite right. Something which absorbs one color reflects the other colors, so it appears to be a mixture of those other colors. So let us now imagine you have treated a sweatshirt with a molecule that only absorbs blue. Whatever that molecule is, right? So you have treated a sweatshirt with a molecule that only absorbs blue, and then you illuminate it with white light. What color is that sweatshirt going to be? Well, the white light is an equal mixture. Here's white. It's an equal mixture of red, green, and blue. it absorbs the blue, so upon reflection over here, you see red and you see green. And the mixture of red and green is yellow. So a sweatshirt treated with a chemical that only absorbs blue under white light illumination will appear yellow. It absorbs blue, it reflects red and green, and the mixture of yellow and green is this area in the middle, which is the overlap of the red and green color circle. So this is yellow, which is the mixture of red and green. If you treat the sweatshirt with a chemical molecule that strongly absorbs red and only absorbs red, that means that that sweatshirt is going to very easily reflect green and blue, which means that to your eye, that sweatshirt will appear cyan. That's what this aqua turquoise looking color is. That's called cyan. Cyan is the equal mixture of green and blue. And in the same way, if you treat a sweatshirt with a chemical that only absorbs green, that means it strongly reflects red and blue. And so to figure that, you go across the color wheel, boom. And that means that this thing to your eye will be magenta. And that's what that pink color is. So yellow, cyan, and magenta, if anyone has ever bought a colored printer, which is probably most of you, the ink cartridges you put in a printer are not red, green, and blue. They are yellow, magenta, and cyan. Those are the three secondary colors, and they come in a printer. They are the secondary colors because think about it. Now you understand, like, why are the three inks in an inkjet printer, why are the three ink colors yellow, magenta, and cyan? Because a yellow ink is an ink which strongly absorbs blue, period. A cyan ink is an ink which strongly absorbs red, period. A magenta ink is a ink which strongly absorbs green, period. So those inks are easy to make because it's a molecule that doesn't have to absorb two colors. It is a molecule that's made to strongly absorb one color, and that they can do really well. And if it absorbs that one color, it reflects the other two, which gives these appearances, right? So those are the secondary colors: yellow, cyan, and magenta. So that's how this color wheel in reflection works when one color is reflected, when one color is absorbed. So when one color is absorbed, say blue, you just go across. Something that absorbs blue is going to appear yellow. It's always on the opposite side of the color wheel. So with these color wheels, you're always trying to identify the color that's absorbed, and then you go across. Right? If it strongly absorbs red, you go across. That means that thing will be cyan. Remember, if it absorbs red and green, two colors go across. Across from red and green is blue. So these color wheels work whether one thing is being absorbed, whether two colors are being absorbed. It works if all the colors are absorbed, which is black. It works if none of them are absorbed, which is white. And of course, it works for any color of illumination as well. It doesn't have to be white light. Now you can start saying, well, if I illuminate it with just red light, what would this thing look like? So you're always trying to understand when something looks like something to your eye, what does that mean it's actually reflecting to you? Do I have questions from anyone on any of this, the stuff about the colors? Okay. So sometimes you will see the color wheel in absorption. So what I was showing before is like the color wheel in reflection. Sometimes they say the color wheel in absorption. It's really the same thing. It's just a different way of looking at it, because now we're talking about absorption. It's the inverse of that color wheel, where now black is on the inside, white's on the outside. The secondary colors are on the outer well of the wing, and the primary colors are the things that are in the overlap region. So yeah, it just kind of tells you what things are being absorbed and what things are being reflected. So again, on the white side, in absorption, if nothing is absorbed, object appears white. If everything absorbed, it's in the middle, it appears black, and then some different combinations, right? So if it strongly absorbs blue, blue, then it's going to reflect green and red, so it'll appear yellow. It's the same wheel. They always sometimes just present it as two, so I show it to you in case you ever see these wheels. They will be shown two ways, as if it's two different things, but it's not, right? If it strongly absorbs green, you just go across, that means it's going to appear magenta to your eye. If it strongly absorbs green and blue, and you go across from that, that means it would appear red. So the color wheels are just, again, I don't use them quite a way in this balancing, but I do use it going back and forth just to remind myself, oh yes, yellow is this mixture of red and green, and cyan is this mixture of blue and green, and magenta is a mixture of red and blue. And once you have that, then you can always jump from one side of the color wheels, either one of them, to the other, to know what it will look like. So the color wheels in absorption and reflection they're just basically showing the same thing. It just depends on how you think about it. But it's just this idea of just remembering, you're always thinking about what does it appear to your eye? If it appears to your eye this color, what colors are present in that, and then what color had to be removed to make that color, and then that tells you what's being absorbed. So it's not that difficult. But color is actually really fascinating, right? There's no doubt about that. So just these definitions. Cyan, what is cyan? It's that aqua turquoise color, the color of a material seen in white light illumination that absorbs red and equally reflects green and blue. That is the definition of cyan. What is magenta? It's the color of a material or an ink that is seen in white light illumination. It strongly absorbs green. Magenta contains equal amounts of red and blue. Now here's a cool thing, if you guys have never seen it. I just throw this in there because I saw this at a conference I was at a while ago, and I thought this was just the coolest thing in the world. So if you ask, like, how black is black? We're talking about absorption. How minimized can you make reflection? All right, so the darkest thing that was made at the time, there actually is a darker thing now, and it's literally changing by the year, so I don't update that so much, is this color called Vanta Black. So what's the blackest thing in the world? Vanta Black, a super black coating that at the time held the world record as the darkest man-made substance, right? It reflects only 0.036% of the light that strikes it. So, I mean, it literally just absorbs everything, which means you just can't see it. It is a void. It is a black hole. So you guys are used to seeing like a black sweatshirt, but you know, a black sweatshirt isn't really black. It kind of looks black, but you can see features on it. What if you could make something so black that nothing bounces off it? Well, this is the closest thing that that they've come up with at the time. So if you look at these pictures right here, there we go, here come my check marks. So that's a bust or a mask of Shakespeare on the left. On the right, it might look to you, because it's not quite as clear on the blackboard as it is on my computer, that kind of looks like a photoshopped image where it's been cut out. It is not. That black silhouette is the exact same bust as what's shown on the left, but treated with this Vanta Black, which actually is carbon nanotubes. So that is not a photoshopped image, although I know it looks like it. That is the real, if you were standing in front of it, this is what you would see. It literally just does not reflect anything. So your eyes don't pick out any of the features, those bumps and those crags and his mustache and his eyebrows and his nose. You just can't see it. And then in the bottom picture, again, it's the same two busts or masks, and they've just kind of turned, they're just taking the picture from the side. So at least from the side, you can see the profile, right? The nose, the lip, the eyebrows, but there's just no feature on it. It is just the creepiest thing I think I've ever seen. It is just so creepy. And in the left, what I'm showing here is a GIF of a YouTube video. So if you just after class, you just want to YouTube Vantablack, and there's blacker, even more blacker stuff now. But this video on the left shows, in the view they're showing now, like, look, they just take a piece of aluminum foil, and you can see the crumpled up aluminum foil, and they've coated the inside on Vantablack. And you guys have all seen a piece of crumpled up tinfoil, right? You know exactly what it looks like. But with the Vantablack, from the front, it looks just like a round black circle. You cannot at all tell that that's a piece of aluminum foil with depth and texture and crinkles and wrinkles or nothing. It literally looks like a bottomless hole into which you will put your arm, and your arm will never appear from it again. All right, so this is what we're talking about with absorption. Can we engineer things that literally reflect nothing and they absorb everything? Well, the scientists are working on it. I don't know what the applications of that are, why you need something to be that black, but I certainly know that it's really creepy. Okay, very good. Let me So does anyone have any questions on any of that? All right, let me just share this for 1 second. All right, so I have to just okay, I have to go back to the reading view. Okay. Oh shoot. Oh, technology is wonderful. All right, I think I have another question coming up for you here, which is why I wanted to. Okay. I'm going to show this. Share that. Stop sharing here. Okay, so we're back to the lecture. All right, so we've talked about color generically. Now I want to talk about color for medical applications. So let us talk about what things get absorbed. So tissue with blood, all right, so let's just think about blood as an easy one. So you've all cut yourself and you look at blood. When you see blood, it appears red, right? Almost all forms of blood are red. So tissue with blood in it, when you cut yourself, is red. That means to your eye, it is strongly reflecting red. So now what you know about the color wheel is if I ask you, like, what color of light does blood absorb? You say, okay, when I look at blood, it looks red. We will use our color wheel. If it looks red, and you go across the color wheel, that means it must strongly be absorbing green and blue, right? Because white light is red, green, and blue. If after the red, green, and blue interact with the blood, all it reflects out to you is the red, that blood must have absorbed green and blue very well. All right, so now when you see colors of something, what it looks like, I want you to think about, well, then if you were illuminating it with white light or any other color, what must it have absorbed to allow that color to be the only color that comes to my eye? All right, does that make sense? So we've dealt with a bunch of kind of generic applications, but now I specifically want to talk about, these medical applications. So blood. Blood is clearly red, so it is going to strongly interact with green and blue light. Okay. Let's go ahead and take a question on that then. So here's a Kahoot question that's going to be coming up. The question is going to be a tissue appears yellow, maybe jaundice tissue is yellow. It appears yellow to your eye under white light illumination. So what color or colors is that tissue absorbing? Let's go. What color or colors? Because remember, some things do absorb more than one color. All right, we had 4 people who said blue, and we had 3 people who said blue, cyan, and magenta. And the correct answer is blue. All right, it cannot absorb cyan and magenta, because what is magenta? Magenta is an equal mixture of red and blue, so it cannot be absorbing magenta, right? If it appears yellow to your eye, yellow is an equal mixture of green and red. Therefore, blue must have been removed. It cannot have absorbed cyan. If it absorbs cyan, that means it absorbs blue and green, because that is what cyan is. And therefore, that thing would appear red. All right, so if it appears yellow, it is strongly absorbing blue, because red, green, and blue make white, and the removal of blue leaves red and green, and equal parts red and green are yellow. That's how you use that color wheel. So clearly I kept asking you guys if you understood it, and half of you were not understanding what I was saying. So you need to make sure you're actually understanding things when I ask those questions, but nobody chimes up. So if you say nothing, you know what? When you say nothing, the assumption is, okay, you completely understand what I'm saying. So there you go. Blue. Blue is the right question. Let's try another one. Question number 3. Kahoot coming up on the left, questions on the right. So an object appears blue to your eye under white light illumination. Now I'm asking you to extrapolate. If you illuminate it with an intense cyan light, what color is that thing going to be? An object appears blue to your eye under white light illumination. That tells you what the material is. Then, if I illuminate it with cyan, what color will you see? Because you can certainly walk into a room with yellow lights, cyan lights, magenta lights, red lights, green lights, blue lights. That's easy. So you have to be able to extrapolate beyond white light illumination. It appears blue to your eye under white light illumination. That sentence, what does that tell you about the material? It tells you something. Then think about it. I now take that thing into a room flooded with intense cyan light. What will your eyes see? Oh, okay. Well, 3 people got the correct answer, which is blue. 1 person thought red, 1 person thought green, 2 people thought cyan. Let's go through the logic. Okay. An object appears blue to your eye under white light illumination. Period. Full stop. What colors does that object absorb? Daniel, you're up. So Daniel, what colors does this object absorb? It appears blue to your eye under white light illumination.
Would it absorb red and green, right?
100%. Thank you, sir.
Yeah.
That's it. So now you have a material that absorbs red and green. That's what it does. You then illuminate it with cyan light. Cyan light is a mixture of blue and green. You are illuminating something that absorbs red and green with light that is blue and green. So now red has nothing to do with it because it doesn't matter that it absorbs red. You're not hitting it with red light. You're hitting it with light that's equal parts blue and green. This thing absorbs green. So if you illuminate it with blue and green, the green is removed. All that's left is blue. You will therefore see it as a blue object, right? So that's why I said it was a two-part question. It is blue to your eye under white light illumination. That tells you what the chemicals in the thing are. Okay, there are chemicals that absorb red and green. But I'm not hitting it with red light, so that part of the question is actually irrelevant. So for the second part of the question, this is now a material that strongly absorbs green. So you hit it with a mixture of light that's green and blue. It strongly absorbs the green. What is left? Blue. Okay? So think about that one if that doesn't make any sense. But it does make sense. Colson and Jordan. All right, Jordan is on fire. Excellent. Here's a question. Now we're talking about the different molecules in your body. What color would melanin look like if we saw it alone? So I'm showing you literally a figure from Kane. It is the absorption spectra of oxyhemoglobin and melanin. She put it into one. Melanin is the dashed line one. You can see it. Now you know about absorption. You know how colors look. I give you the color wheel underneath. You know how it absorbs. And I ask you this because Kane talked about this, not because I would expect from the previous 15 minutes of conversation you would get it, but from the 15 minutes of conversation and your reading with Kane, what color would melanin look like if we saw it alone, given this absorption? Okay, 5 people said 4, and then 1 each for greenish yellow and bluish green. The correct answer is 5. All right, reddish brown, and she specifically said that in the text. I mean, 1, she said it's reddish brown. 2, you should know that melanin is the pigment in our skin, and there's not a whole lot of violet, blue-green people wandering around. So again, you should have got that from the reading. So if you're reading this whole unit and it had multiple references to melanin, and you have no idea what melanin is, then you're not critically reading. You're just not, right? Melanin is the pigment in the skin. So if I just ask you on general, what color are humans? All humans. All of us have melanin as pigment in our skin. What color are humans? And if you're telling me, so no offense to the person who answered number 2, you're saying most humans are bluish green in hue, I would say no. Marvin the Martian from Bugs Bunny, maybe. Are humans greenish yellow? No. Are we violet? No. What color are most people? Kind of reddish brown, right? Caucasians are more palish. Asians are more in the middle and other different, right? But all humans, all of our skin colors are all reddish brown something. So you know that without even the color wheel. So you could know that if you know what melanin is. It's the chromophore, which is the word for the molecule in your skin that's interacting with the colors. That's the color that humans are. But then, of course, we have this color absorption wheel here. The absorption of melanin is low out in the red colors, and it gets higher, 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 all the way out to the blue colors. So it's not a specific color, but clearly this molecule absorbs yellow more strongly than red. It absorbs green more strongly than yellow. It absorbs blue more strongly than green, and violet more strongly than blue. So all those blue-green colors are all gone, more than the others. It's not 100% absorption, but they're gone. So the thing that is absorbed the least is reflected the most, and in this graph, the thing that is absorbed the least is out on this end, which is 600, which is red. All right, so these questions, there's always a couple ways to get at the answer, using your knowledge of physiology, but also just using what we've learned in this class. All right, so that's that. Well, let's see, I am a huge believer in redemption, always. So let's take another one. Which of these 3 laser wavelengths shown would be best for laser surgery on skin, which contains a large amount of melanin? Again, it's a figure from Kane. I'm not springing new figures on you. You should have seen this figure. You read about it. You should have thought about it. Why did she include it? What does it tell you? We just talked about melanin. We talked about the color that melanin has. Okay, so 7 people thought it was 488, which is the correct answer, right? So now we're talking about when we understand the mechanics of absorption now, and now we understand what does absorption have to do with laser procedures. We want the laser to interact strongly with the tissue. So I gave you 3 different numbers, 488, 514, 577. You looked at the graph, this melanin absorption curve, and you know for a medical procedure, you want the color that absorbs the most. That's the reason you're shining the laser in. You want it to absorb. You want it to do something. You want it to cut. You want it to coagulate. You want it to heat. It has to interact, and the stronger it interacts, the better. So all other things being equal, you just pick the thing that has the strongest absorption. And because melanin just keeps getting stronger and stronger absorbed, the more ultraviolet you go, you all pick the color that was the most blue, which is 488 and 100% correct. Absolutely right. Perfect. Very, very good. Everybody's doing fantastic today. This is a great way to wind up on Friday. Here's a question for you. Which form of hemoglobin appears more blue? Think physics and think anatomy. I actually knew this question before I started teaching this class. I don't care how you know it, as long as you know it. So you might know the physiologic answer for this. You might know it just from the reading with Kane. You could now figure it out from just this graph. Medical people will know this, nurses will know this. So 7 people said number 2, which is the deoxyhemoglobin, which is of course the correct answer. So we know that arterial blood, which is coming from your lungs, has oxygenated hemoglobin, and arterial spray and arterial bleeds are always very bright red, very bright red. Blood that has had its oxygen removed has the deoxygenated form of hemoglobin, deoxyhemoglobin. It has venous blood, it is blood returning to the lungs, and venous blood is always very dark purple in color. It really is, I mean, arterial blood and venous blood, it's very easy to tell the difference on with your human eye, easy to tell. And that all has to do with whether the hemoglobin is carrying oxygen or not. And of course, the absorption curve tells you that that is true. If you look out, so which appears more blue, you go out into the blue colors, which are on this end of the spectrum. If it appears blue, it clearly cannot absorb blue, right? So you want the thing who absorbs blue less. So the deoxyhemoglobin is this low curve. So out here, there's 2 curves. Whichever one absorbs blue worse is going to be more blue. That's this curve. That's this one humped curve, and that's deoxyhemoglobin, right? And it also tells you why oxygenated blood, arterial blood, appears more red. Well, red colors are out around the 600 nanometers. So if it appears red, it will absorb red not at all. And note, on the red end of the spectrum, the deoxyhemoglobin curve is way lower. The oxyhemoglobin curve is way lower than the deoxyhemoglobin curve. It does not absorb red at all, which means it appears very red to your eye. Okay? So, and you might have, like I said, you might have known that from anatomy, which I did before this, but now you can also get it from these curves, and you can start to make some sense of what you kind of know for sure. That was a great job today. I'll let the podium come up on the left. So I would just say, know your chromophores, guys. There are not so many chromophores in medical physics, but kind of what I want you to know is these fundamental laser wavelengths, the argon ion at 488 nanometers, frequency double YAG at 532. I'm kind of showing representative colors on the screen. Krypton red at 647. Here's this infrared YAG at 1064, and here's carbon dioxide way out there. Some of the primary chromophores in your body are hemoglobin, which we just talked about, that has this absorption curve that just does this, and then water, which has an absorption curve that looks like this. So if you want an application, that chromophore needs to strongly absorb that color. So for operating on things that have a lot of blood, a lot of hemoglobin, something that's green or blue or violet would be great. A red laser would be a horrible choice. If you're operating on something with water, clearly an infrared YAG laser would not be such a great choice because water doesn't absorb strongly, but CO2 way out here at 10 microns is strongly absorbed by water, so it cuts really, really well. There are just not a lot of other chromophores to know that I know of. So here's a better one that kind of has, so here's melanosome. That's essentially the melanin we were talking about before. Oxygenated blood, deoxygenated blood is here, and then water is here. So I found Kane's figure to be a little bit crude. This one I'm showing on the screen shows a little more of the fine detail. It gives a couple more of the laser wavelengths, and it gives the absorption curves of water, oxygenated blood, deoxygenated blood, and melanin. So there's 4 of them. That's about all I know. Here's a graph down here that I pulled off the internet. Again, it shows melanin, oxyhemoglobin, and water. And porphyrin, but I'm not exactly sure what that chromophore is. So it's not like your body is swimming with dozens of chromophores. For you as a medical physicist, if you know like blood, it's oxygenated and deoxygenated state. If you know water and if you know melanin, you're pretty good. We could talk about adding chromophores to a patient to make them light sensitive to a certain wavelength, which they certainly do, and those are very cool applied laser applications. So in our next lecture, we're basically done for today. In our next letter, we're going to get into medical applications. All of them are going to involve these colors. So now you understand the colors, and now you say, now what can we do with these lasers? Well, you can do cosmetics, huge number of dermatological applications, tattoos, scars, stretch marks, sunspots, wrinkles, birthmarks, hairs, spider veins, things like that. All of those colors you're going to want to be absorbed in the skin. So they're all going to be kind of, these ruby lasers, alexandrite, infrared, things that are absorbed right on the surface so much. Eye surgeries, we're going to talk about LASIK, PRK, cataract removal. We'll get all into that on Monday. Laser scalpels, these CO2 lasers, which cut through everything. Very commonly used gynecological, urological, laparoscopic, things like that. Removal of tumors. Here's one thing else we didn't talk about. A laser, when it's shining on you, you don't feel anything. So when they're doing very careful removal of tumors around the spinal cord, those surgeons worry a lot. One little slip around the spinal column and a patient can be paralyzed for life. The laser never touches anything, right? It is like zero touch, and so you have really exquisite control of how you're removing tissue. Dental procedures, really good applications we're going to see where you don't have to drill into teeth. Imaging, photoacupuncture, biomodulation. This is not a complete list, but when you talk about lasers and light in medicine, the number of applications are literally dozens and dozens and dozens. All of these units, again, probably used by an MD, dentist, pharmacist, not pharmacist, but veterinary, but the units made by physicists, right? Doctors don't make the lasers, they just buy it. So are there jobs at companies for people who build all these surgical laser units? For sure there are, and they would hire laser physicists and engineers. This is another type of career that you guys might be preparing for, because as these applications become more common, these units, which are very expensive, are going to need people to build them. These companies are going to need employees. So that's just one area that a medical physicist could go into. We're going to come back to this slide. This slide would be a good thing to kind of have. We're going to talk about this in the next in the next lecture, but this is table 3.2 from Kane. This is table 21.2 from Pedrotti. The type of questions I like to ask are in general, like, you know, do you kind of know the laser and the color and what it's used for? Is it CW or pulse? What is its gain medium? We're going to go through all these on Monday, but it's only one day. So you should kind of start looking at these, have this thing handy. You know, like if I ask you what kind of laser is used in the eye, you're going to want to be able to answer that. You know, you're going to want to know that like a ruby laser is a deep red laser. You don't, you know, you have to be able to remember, and it maybe is used for tattoo removal, things like that. Don't worry about the power and the energy. That I will never ask you. So power and watts, because those things are all variable. I'll never ask you that. But I do kind of want to know an excimer laser. You should know what wavelengths those things operate at and what it would be useful for. Right? If I said there's an argon ion laser, what color is that? And what applications could that be used for? So we'll go through them all on Monday, as many as we can, but I do like to ask questions about these kind of in general, just so you have a passing knowledge of what those things are, okay? So we will see this again, but these two graphs, these are things that I would kind of want you to know, and you know that they're common: argon, argon, ion gas, CW, CW. I like this one because it tells you whether it's like a solid, liquid, gas, solid, solid, gas. I like this here. Kane doesn't tell you that. But between the two of them, you're going to really know everything about any laser you might ever encounter in your medical career, which will be fantastic. That's it. This is just that graph of oxyhemoglobin. Okay, so that's all we have for today. Have a great weekend. I'm going to try to get to your homeworks. I don't think I'll have them graded all by Monday. I'm going to try to get into it as quick as I can. I have some other stuff I have to be working on the weekend, but I will try to get those returned. And we'll have one more follow-up lecture on Monday for the laser applications. So have a good weekend. I will see you on Monday. And I will stop recording now.